Good morning and welcome to webinar 15 of the Powerful Knowledge series. Today, Jose is going to be talking all about condition monitoring in power electronics. And it's a very interesting subject because it ties into reliability, lifetime of products, all that sort of thing. It's a very interesting area. So if you've joined us before, this is webinar number 15. We've covered lots of areas in the past. The format of these webinars is that the technical presentation lasts for about 1 hour, after which we'll be hosting a Q&A session. If you do get questions on the content as we're going through, please enter those in the questions box, which you should see on your screen, and we'll go through those at the end. Today, I'm going to be looking after the chat box side of things. So if you have any problems at all with the sort of the technical the way the webinar is working or access or the video, that sort of thing, let me know in the chat box and I'll try and help out if I can. Jose will be doing the presentation today, and then throughout the presentation we're also going to be launching a number of polls to help us understand whether you're engaging with the information, whether it's interesting, and the sort of background of you as the audience participating in this today. So without any further hesitation, I'd like to welcome Jose and hand over for his presentation. Thanks, Jose.
Hi, Ian. Thanks for the presentation, for the introduction. I'm going to disable the video and start the presentation now. So bear with me. Slideshow. So today I'm going to present a webinar called Condition Monitoring in Power Electronics, and it links to my previous webinars. I'm going to base it on Silicon Carbide. So this is just the outline of the presentation. So we start with an introduction, then we explain a bit the challenges of power cycling in Silicon Carbide MOSFETs to conclude with my previous webinar on packaging, but this time focus on Silicon Carbide MOSFETs. Then we evaluate some of the most common circuits for condition monitoring, and we conclude the technical part of the presentation, evaluating the impact of VTI on condition monitoring for Silicon Carbide MOSFETs, and then we just conclude the presentation. So, understanding how the power device and modules degrade and how the electrical parameters are affected is fundamental. So this information can be used for asserting the state of health condition of power devices, modules, systems during normal operation. That's what you want to know. You want to understand how your module is affected by lifetime degradation. And this has raised the topics of condition monitoring in power electronics that they have associated other topics like failure-safe operability, redundancy, prognosis, preventive maintenance, and this is quite important. There are a lot of people working on these topics. So the first thing that I would like to highlight is what are the benefits of condition monitoring. So I just took some data from a report that is online, the case for condition monitoring, and they evaluate the impact of condition monitoring on industrial plants. And they report a reduction of 30% of maintenance cost, an increase of 30% of the lifetime, a reduction of 40% of the downtime, and an increased availability of 30%. So that's good. That means less costs regarding maintenance and downtime, and it means increasing reliability and availability of your system. So that's good from the point of view of manufacturers, of end users. So that's why people want to implement condition monitoring. So something that is key for implementing condition monitoring is temperature, namely the temperature of the chip, and the ability to identify the chip temperature, which is related to the state of health during operation, can enable damage assessment, lifetime improvement. You can also define operational constraints. So you can say, okay, my device is getting hot. I don't want to this temperature to go this high. I think that my power module is damaged. It's time to replace it. So that's why this managing and identifying the state of health, the chip temperature is important. And to that end, laboratory power cycling tests are key because they give you a feeling, they give you an understanding, they explain the underlying failure mechanisms. So you can do this in the laboratory. So it's usually called offline. And you have a wide range of equipment available for that end. So you have scopes, voltage probes, current probes, you have thermal cameras. So in the laboratory, it's really easy to open a module and check the temperature of the chips during operation, how they evolve because of the different power dissipation. So you can measure things easily. You have access to everything that you want to measure. But to implement things online during the application, things are way more complicated. So you just have your module, and sometimes it's in an enclosure. You don't have access to the terminals. You cannot remove the case. There's a gel inside, so things are really complicated. So in the application, there is a trend that consists in using temperature-sensitive electrical parameters for implementing condition monitoring. So these parameters are function of temperature, and as I mentioned before, if temperature is changing because of degradation, because you are operating beyond the limits, these parameters are going to change, and monitoring these parameters can be really important for condition monitoring. And it's also really important for power cycling, as temperature is a key parameter in power cycling tests. So just to continue, there's a strong link between junction temperature and packaging degradation. So that's the thermal resistance degradation. And there's an increased thermal resistance due to packaging degradation. It limits the heat flow and the chip temperature increases. So that's why the chip temperature is important and why you want to monitor that. Moreover, measuring electrical parameters can be fundamental for implementing condition monitoring. So you have parameters that are going to be temperature dependent, and you also are going to have some parameters that are electrical degradation dependent, packaging degradation dependent. So if you manage to monitor parameters which are related to temperature or electrical degradation, you are able to monitor the state of health of your power module device. In webinar 11, that was packaging of power semiconductors, the role of power cycling tests was presented, and I focused mainly on silicon devices. And it was concluded that these tests are key for understanding the packaging degradation and failure mechanisms, and they are good for understanding the lifetime constraints, to understanding the lifetime of the packaging. But there are some issues there. You have plenty of information available for silicon devices, but the information regarding power cycling of silicon carbide MOSFETs is not that extensive. There is limited information. It's improving. Now you have way more power cycling results of silicon carbide MOSFETs, but it's not as extensive as the amount of information you have for silicon devices. And one of the challenges was developing suitable methods for power cycling silicon carbide MOSFETs. And this has been a key research objective, and there are different groups that have been working on that in order to design and develop a suitable power cycling method for silicon carbide MOSFETs. So let's start with that and evaluate what are the differences between power cycling silicon devices and silicon carbide MOSFETs. So this is just a brief reminder of DC power cycling, which is widely used, but I just want to make a brief description. So in DC power cycling, you use a controlled heating current to heat up the device. So when the auxiliary device is on, a heating current increases the junction temperature, and then you use a small sensing current for determining the junction temperature using TSCPs, which is usually the on-state voltage at low current. So you monitor the cooling phase, and you have your delta T, you have your cycle. You just require a calibrated TSCP, and that's it. You are ready to stress your device and get your lifetime number of cycles to failure. So before going into silicon carbide MOSFETs, let's analyze a bit what happens with MOSFETs. So I mentioned that you can measure the on-state voltage at low currents, so during the cooling phase. But in silicon MOSFETs, let's analyze a 1200 volts, 20 amp silicon MOSFET, and consider that you have a several milliamp sensing current, let's say 50 milliamps, a low on-state resistance in the range of 500 milliohms. Assuming that the resistance doubles with temperature, your range for the your measured voltage range for the whole temperature range is going to be 25 millivolts, which is not the best resolution range for measuring temperature. So your measuring state voltage is going to be low, and this means lack of accuracy for determining your temperature. In silicon carbide, this range is even lower. So in a 1200 volts 19 amp silicon carbide MOSFET, the on-state resistance increases from 130 milliohms to 200 milliohms. And as you can see here, your whole range is just around 4 or 5 millivolts. So if you want to have a good temperature measurement on the on-state resistance using a low sensing current, this is not good. You are not going to be able to monitor your temperature properly using this parameter, the on-state voltage at low currents. So that's not good from the point of view of power cycling. In silicon MOSFETs, people propose to use the body diode for power cycling, and it can be used for both heating and sensing, or only for sensing. So you have more information in this application note from BSHI. And that looks that this has been accepted and looks okay. It's a good methodology for power cycling silicon MOSFETs. But what happens with the silicon carbide MOSFETs? So unluckily, it's not as straightforward as the case of silicon MOSFETs. There are some things that you have to consider before implementing a power cycling methodology in silicon carbide MOSFETs. So there are some peculiarities of silicon carbide MOSFETs that can affect power cycling. One is bias temperature instability, BTI, and BTI-induced threshold voltage shifts, and bipolar degradation. Key to power cycling is avoiding additional degradation mechanisms. As power cycling is an accelerated test, you don't want to add any other mechanism rather than temperature and the thermomechanical stresses. And it's important that your TSEP is consistent and accurate during the whole power cycling test. You want to be sure that you are measuring the right temperatures during the whole duration of the test. So let's start with the gate stress. So in power cycling, the gate can be on for several weeks, and the device, hence, is going to be biased for a long period with a constant gate voltage. If we just refer back to webinar number 8, we have BTI-induced threshold voltage shifts, and because of the shift of the threshold voltage caused by the gate stress, you're going to have shift of the transfer characteristics, and you're also going to have an increased on-state resistance. So this will affect the power dissipation during your power cycling test as the on-state resistance is going to increase. Body diode, so if you use the body diode as temperature sensor, BTI is also affecting the third quadrant characteristics. So positive stress means a positive shift, an increase of the third quadrant voltage, and this will affect your calibration curve of the body diode as TSEP if you're using a gate voltage of 0 volts, which is what people use for silicon MOSFETs. But as was mentioned in the webinar number 8, if you bias your gate with a negative voltage, you minimize this positive threshold voltage shift, and your TSEP is still accurate and good to measure temperature. So you can consider, okay, let's use the diode only for power cycling in silicon carbide MOSFETs. However, you have a problem that is called bipolar degradation. So it affects bipolar devices, so namely the body diode of a silicon carbide MOSFET. It's related to material defects, basal plane dislocation, and it means that when you have a current flowing through your device, the voltage across the body diode will increase, and it's more strong at high current densities. But it's still, in some cases, at the sensing current, you may have a small shift, and that has been evaluated in these publications here. So they evaluated the effect of bipolar degradation on temperature estimation. So they say that the current density is really important, so you have to be careful with that. Silicon carbide chips are really small, and what you think that is probably a low current density is not that low. And they also evaluated the phenomenon of bipolar degradation in this paper. So you can check these papers to get a feeling of what's bipolar degradation. And I just found a link recently, and they also mentioned that the on-state characteristics are also affected by bipolar degradation, and they report clear differences between devices from different manufacturers. So if you can check this link, you will see that some devices are the on-state characteristics are also affected by bipolar degradation. So with all this is a recommended power cycling topology for silicon carbide MOSFETs, which is just the basic DC power cycling setup. For heating, you're going to use the nominal positive gate voltage, so use the channel for heating up the device. And for sensing, you use a negative gate voltage, and you use the voltage across the body diode, so just to ensure that your TSCP is not affected by BTI. There are some publications that you can check the whole circuit. This is just a simplified schematic, but you can check these publications where they analyze the implications of this topology and how to design effectively power cycling circuits for silicon carbide MOSFETs. So I have a question one number now, that is if you have used power cycling for silicon carbide MOSFETs. Thanks. But now I will just like to make some remarks regarding power cycling in silicon carbide MOSFETs. So remember that in power modules, you have anti-parallel silicon carbide Schottky diodes, and the sensing current will flow through the Schottky diode, which is a problem if you want to measure the temperature of the MOSFET. So in the laboratory environment, some people have used fiber optic sensor for measuring the chip temperature. You can check some references there, how they managed to identify that out. Remember that in power cycling laboratory test, the key is the temperature. And they also have done some modifications, like removing the silicon carbide Schottky, just cutting the wire bonds. You want to evaluate the packaging of the MOSFET, you want to evaluate the MOSFET, you don't care about the Schottky. So you have access to the packaging, just remove the silicon carbide Schottky from the current path and you are good to go. So these are some tricks that you have to be careful when you're doing power cycling on silicon carbide MOSFETs, that is not like a diode or an IGBT. So after explaining this, let's start with some circuits for condition monitoring. So here we are using, let's see, the on-state voltage to monitor temperature, but there are more parameters that you can use for monitoring the state of the device. So you can use different circuits, different topologies, different parameters. So I'm going to cover some of the most common in this section. So as mentioned, during power cycling tests, electrical parameters are monitored to track the degradation of the power device module. And you can do this at device level. So you can monitor the threshold voltage, switching rates, delays, on-state resistance, or you can do this at package level. So the degradation of the wire bonds and thermal resistance. So you can monitor how your system is degrading at both device level and package level. The important thing now is that you require measurements. And these measurements, they are both required for offline and online condition monitoring. So if you want to do that during operation, that's online. If you want to do that during standby phases, during idle periods in the lab, that's offline. And you can use electrical parameters as junction temperature sensor, or you can just monitor changes in electrical parameters caused by damage. So the most common, let's say, what is also used for power cycling is the on-state voltage. So this is widely used during power cycling tests with IGBTs, diodes, MOSFETs. It can be measured at low currents or at high currents, and it requires calibration or normalization techniques. So you can just see here the normalized on-state resistance of different MOSFET devices. You can see that silicon devices, it increases a lot, and silicon carbide, it depends on the generation, but it's not as temperature sensitive. But you don't have to worry only about measuring low on-state voltages. The devices not only conduct current, so low voltage on-state, they have to block voltages, which is usually the discipline voltage, and that's a high voltage. So you can just see here the transients during a double pulse test. And you can see when you turn off your device, you go from a very low voltage on state to a high voltage at 400 volts. And opposite, in turn on, you go from a high voltage to a low on state voltage. Now, you are really interested in monitoring this voltage here. That's what is going to determine your on state resistance. That's what you want to monitor, but you have to worry about these 400 volts. So you are probably not going to have good resolution there. So how can we implement some protection? Because you don't want to connect 400 volts to your measurement circuit. With an oscilloscope, that's fine. But if you want to connect this to your data acquisition system, you need some circuitry to cope with these voltages. And I'm going to present some circuits that are based on that. But first, let's analyze why we cannot use high voltage. So laboratory measurements, they use high voltage probes and oscilloscopes. And for monitoring the on-state resistance, resolution is key. So you can check more details in this paper. And it's an open access paper. So imagine that you have 1,000 volts blocking voltage and your ADC resolution is 12 bits. So the resolution for measuring this 1,000 volts is going to be 250 millivolts. So if you remember when I was mentioning that your voltage, on-state voltage, is going to have a change of some millivolts, you are going to lose all the accuracy of your on-state voltage measurement. So using this kind of laboratory setup, high voltage probes, for monitoring the on-state voltage when you are operating in a converter with high voltage and low voltage, that's not good. And different circuits have been proposed, and key parameters are bandwidth and resolution. And I would like also to highlight that these parameters are also key for determining dynamic RDS-on in GaN devices. So that's something that happens really fast after you turn off your device. So you have the same requirements of bandwidth and resolution. So the first and most obvious is just using a relay for this connection. So your device is operating, and you just use a switch, a relay, and so you isolate the high voltage, and you just worry about measuring when the device is on. And that's when you measure your on-state voltage. That's a good option for offline condition monitoring. You just rely on the response time of the relay. You need specific routines for measuring, and they should be independent of the converter operation. And you require ADC and isolation circuitry for connecting this circuit to the main acquisition system. So you have some references where this circuit is described, but this is just one of the first circuits used for monitoring the on-state voltage. It has some issues like the response time, and you are not always connected to the system. But people decided to work more on this. They like to monitor the on-state voltage, so they propose more circuits. So another one is using an auxiliary MOSFET as emitter-follower circuit. That's MOSFET Q. And the references where they describe the circuit is here. I'm just going to make a brief description to avoid going into the details and make the presentation way too long. So what happens when the device under test is on? The voltage across this resistance is equal to the on-state voltage of the device under test. And when the device under test is off, this MOSFET is almost off, as reported there. And the high voltage is going to be isolated from the measurement circuit. You're going to measure a voltage equal to 9 volts minus the threshold voltage that is on the resistance. So the MOSFET Q has some requirements that it should be able to block the same voltage than the DUT, and it should be a fast device with low parasitic capacitances. And the resistor R is you should avoid excessive power dissipation in the resistor. You don't want the resistor to get hot and affect your measurement system. As I mentioned, you can check the details in these references. This circuit has also been used for monitoring the on-state resistance in silicon carbide power MOSFET. So I just recommend you, if you are interested in this circuit, to check the bibliography. You can also use a clamping zener. So is similar. You want to monitor the voltage across your device under test, and you have just a clamping sensor. This sensor will clamp the maximum voltage that you're going to measure. So this is a slight modification. I will explain later why you require this diode. So if the voltage, drain source voltage is higher than the sensor plus this diode, the voltage is clamped and you measure that voltage. If the voltage is lower than this clamping voltage, you're going to monitor the on-state voltage. So you have the time response of this circuit is determined by the resistance R and the parasitic capacitances of the sensor and the diode. And this is why you have this diode here. So you have this combination of sensor and diode, you reduce the parasitic capacitance. So you have two capacitances in series, your circuit is faster. And something important here is the voltage rating of the resistance R. So this resistance should be able to operate at the maximum VDS voltage. So more details of this circuit and how the parameters are calculated, response times are given in these two references. So another circuit that is also used for monitoring the on-state voltage is using a depletion mode transistor. So it's a Q. It's a normally on depletion mode transistor with a threshold voltage lower than 0. So you just require some clamping diodes and a clamping voltage that should be greater than the on-state voltage of the device under test. So when your device under test is on, there is no current flowing through the transistor Q. Your gate voltage of Q is 0, so this transistor is on. Remember that it's a normally on transistor, and the voltage that you're going to measure is the on-state voltage of the device under test. When the device under test is off, VDS is higher than the clamping voltage, so there's going to be a current flowing through Q. So this means that the gate voltage of this device is going to be negative. This transistor is going to switch off, more or less. And the clamping voltage is going to be measured in this period. So you have a small current flowing through this resistor and these clamps, and you measure the clamping voltage. The good thing of this circuit is that during the body diode conduction, a negative voltage is measured. And you can use different MOSFET cells in series to increase the blocking voltage. So you could use this circuit for very high voltages. So you have some references here when the circuit is proposed and analyzed. And also, I particularly like this, where they evaluate how to implement this circuit for monitoring a wind turbine in the application. So if you have time and you are interested in this kind of topic circuits, just go through the bibliography and you will understand the details of the circuit and how it operates. And this is a circuit that has been quite successful and is widely used by different people. That consists in using auxiliary diodes for monitoring the on-state voltage of the device under test. So key here is that you have some amplifiers and some diodes to block the high voltage and measure the on-state voltage across the device. But you could see, okay, but the circuit is measuring the voltage across the diode number 2. It's not monitoring the voltage across the MOSFET. So why? I will try to explain that. So just bear with me for a moment. So important thing is that diode 1 is used for blocking the voltage. There's an additional anti-parallel diode here to be sure that all the voltage is only blocked by diode 1. And when the device under test is on, there's a sensing current that is defined by this current source that will flow through the device under test through the MOSFET. So that's just the on-state operation, but let's analyze this in more detail. You have references here where you can check how the circuit operates and how it's used and how they monitor the on-state voltage of devices. But let's explain how it operates. So during the on-state of the phase of the MOSFET, the voltage can be measured using the diode. So I'm going to explain why. So first, let's assume that both diodes are identical and they have the same temperature. So the voltage drop across the diodes can be called VD. I define just 2 points, A and B. And the on-state voltage of the MOSFET is voltage B minus voltage at the drain VB equals VA minus VB. So V on equals 2 VB minus VA, just substituting on this point on this equation. So let's analyze the operational amplifier. So you have VA minus VB over resistor 1, VB minus V out over resistor 2. Assume that the resistances are the same, and just get VA minus VB equals VB minus V out. So you just put V out on the other side, and V out equals 2 VB minus VA. So this is quite interesting, that just monitoring the voltage across this diode, you manage to monitor the on-state voltage of the device, and at the same time with this circuit you are isolating your high voltage from your measurement circuit. So once now that we managed to measure the on-state voltage, something that I would like to remark, that in order to use the on-state voltage as degradation cursor, the current has to be known and fixed. And it may be DC current or AC current, but remember that the on-state voltage is also current dependent. So if you are just monitoring randomly the on-state voltage during operation and your current is changing, your on-state voltage is going to change. So if you want to use the on-state voltage, you need a known and fixed current that can be both DC or AC. But you can decide, I want to measure the on-state resistance. But for measuring the on-state resistance, it's fundamental to measure the drain current. So different sensors are available, and you can use shunt resistors, magnetoresistive sensors, Rogowski coils, Hall effect sensors. So if you have your on-state voltage and you have your current, you can calculate your on-state resistance. Let's focus now on silicon carbide MOSFETs. So referring back to webinar 5, the channel resistance plays a fundamental role, and it is a main contributor to the total on-state resistance. So when you are measuring the on-state voltage across the chip, the on-state voltage across the packaging, you're measuring the voltage across the chip and the packaging elements. But what you really want is the voltage across the chip, and you want also to decouple the voltage on the chip and the voltage on the packaging elements. So this can be really important to understand what is degrading. Is the chip degrading because of gate oxide? Reliability issues, is just packaging degradation, so this can be really important for silicon carbide MOSFETs. And no, this can be done because of the emergence of 4-pin TO247 packages, so that's also already available on power modules. And if you have this Kelvin source available, this is quite important because you can monitor the voltage drop between the Kelvin source and the drain, which is just the voltage on the chip, and you can also monitor the voltage across the Kelvin source and the source, which is the voltage across the source wire bonds, and you can identify both voltages. You can just use this circuit to monitor the on-state voltage and amplifier to monitor the voltage across the wire bonds, so you can track what is degrading. Is the MOSFET voltage degrading? Are the wire bonds being damaged? So this is quite an important circuit that I consider an important option to evaluate what is degrading in the case of silicon carbide MOSFETs. This is also an open access paper where they propose this circuit and they have some results. So you have time and you are interested in the topic. This open access paper is quite interesting. And I would like to highlight that this is really important for silicon carbide MOSFETs because of the PTI-induced threshold voltage shifts. So if your threshold voltage shift is changing, your on-state resistance on the MOSFET is going to change, but your wire bond resistance is not going to change. So you can track parameter variation using this methodology, this topology, for measuring both the chip voltage and the wire bond voltage. And another parameter that you can use for tracking, for condition monitoring, is the threshold voltage. Threshold voltage is a well-known TSP that reduces with temperature. It's just the gate voltage that you require to invert the channel. It has this expression. It's just a textbook equation from Baliga. It's a basic book of power semiconductor devices. There are different ways of determining it experimentally, and one that is quite common, that is reported on the datasheets. You just connect the gate and drain, you force a low current, and that the voltage that you apply at the gate for that determined sensing current is your threshold voltage. But how can you do this on the application? Can you just connect the gate and the drain and monitor that? So that's tricky, or let's say impossible to do in your converter. If you would like to monitor the threshold voltage shift, you will need some additional circuits, some methodologies to monitor the threshold voltage. So something to do this during operation is just measure the gate voltage and the drain current. So when your device starts to conduct, if you manage to measure the gate voltage and capture, you will identify what your threshold voltage is. It's just the moment when the current starts to rise. You will require high-speed measurement circuits. So you have to sample the gate voltage with a very fine resolution. And also you will have to measure the current with a fast resolution, fast timing. You have to detect just when the current rises, and then you just detect current rise. You are sampling the gate voltage. That's your threshold voltage. It's not dependent on the load resistance and the load current. Sorry. You require a large gate resistance for slowing down the switching transient. So this time, T0 to T1, that delay. If you increase your gate resistance, you're going to increase your time for sampling, your resolution. So you don't want this to be 1 nanosecond. You want to have a large time to improve your resolution for measuring VTH. Still tricky. You require the measurement of the current. You require high-speed measurement circuits. So some people have proposed alternatives. And some people propose the quasi-threshold voltage measurement, which consists in measuring the gate voltage and the voltage across the parasitic source emitter inductance. So you don't require a current sensor. You are going to use the voltage across the source inductance. So let's analyze this a bit. So you have your transient that you're measuring with your gate source measurement circuit, and you just have the drain current transient. As you are measuring the source inductance, the parasitic source inductance, this current transient causes a parasitic voltage that is related to the current, and you can use this auxiliary signal for sampling the gate source voltage. So if you just use some additional circuitry comparators on this voltage, parasitic voltage, you can get a trigger signal which is related to the drain current transient, and you can use this trigger signal to sample the gate source voltage. So this is why it is called quasi-threshold voltage. There's a small delay of the comparator. It's not just when the current starts to rise. You just use that comparator, and you can use this if you have access to the source inductance. This circuit, which is defined here, can be used for sampling the threshold voltage during operation. I would like to say that this circuit has been quite successful. Some people have implemented this methodology for monitoring threshold voltage. So you have some references here that you can check how they implemented this circuit that was proposed here in this reference. So it's always interesting to see how people use other circuits defined by other researchers to implement their condition monitoring techniques. Also, another TSCP is the switching rate of the drain current. So the drain current switching rate at turn on is a TSCP in Silicon Carbide MOSFETs. So you have an explanation in this paper. And this is just the equation that determines the temperature sensitivity. You can monitor this, measure this using a double pulse test setup, and you can see how the switching rate increases with temperature. So you have your TSCP. Let's check how you can use this TSCP. The temperature sensitivity is affected by how the device is driven. So the temperature sensitivity increases with gate resistance and reducing the gate driver voltage. So if you switch your device slower, your switching rate, the temperature sensitivity of your drain current switching rate is going to be more apparent. So you can see it here. If you're driving your device with 20 volts and 47 ohms, temperature sensitivity is there. But if you slow down your device with a gate driver voltage of 13, you can see that temperature sensitivity more clear. Now, I would like to highlight that it's important to consider the difference between absolute and relative temperature sensitivity. So this is just a small study that is, we switch the device with 47 ohms and 220 ohms, and we just at different gate voltages. You can see that if you switch your device with 20 volts and 47 ohms, the increase of the switching rate is around 11% with a temperature coefficient of 0.24 amps per microsecond per degree. Or you start reducing the gate driver voltage, the normalized increase goes from 11 to 26, but the temperature coefficient is reducing slightly. So your increase is going to be more apparent, but the way of measuring it is going to be not as temperature sensitive. So your coefficient is going to reduce. Let's now reduce further the switching rate. So now we are switching with 220 ohms and 20 volts. So you can see how the normalized increase now is 14%, but your temperature coefficient has reduced quite considerably. Now you just reduce the gate voltage, and you can see, okay, I have a normalized increase of 32%, which is good, but now your temperature coefficient is going to be really low. So this is bad if you think about, to say it plainly. So the impact of temperature is more apparent, but this is going to be way more difficult to measure. At the end, what you are going to measure is the variation of the parameter with temperature. So it doesn't matter if it increases 100 to 200% if your variation is just a few millivolts. So this is also something important when you are analyzing TSEPs and parameters, that is not only a normalized increase. So something can double and go from 1 millivolt to 2 millivolts. But if you have to use that millivolt to get the whole range of temperature, that's going to be complicated from the point of view of instrumentation. So some people propose some circuits to use this parameter, and they use the stray source inductance or a Rogowski coil to measure the drain current switching rate. They propose a peak detector, an operational amplifier, and they were quite successful using this circuit with the right rate with the right switching rate and with the right gain and this circuit design. They managed to monitor variation of voltages from 0.4 volts at low temperature and 0.8 volts at high temperature. So if you have some circuit and you have some workarounds, you may be successful exploiting the temperature sensitivity of determined parameters. So this paper is open access and you can see the details of the circuit. So sometimes it's not only having the parameter there, you need the right circuit to measure your TSEP. Other parameter that is quite successful now is the internal gator systems. And, there are a lot of people working on the internal gator systems of IGBTs and MOSFETs as TSEP. So internal gator systems, it appears on the datasheets, but I would like to say that it's very important to verify if it is internal or it's an additional resistance. So in case of some modules, some manufacturers, they add additional resistances to balance the switching between parallel chips. You can read more about this TSEP in this publication, and it's important that it's the resistance, the internal gate resistance on the gate. So it's just something that is within the chip, it's not external to the chip. So monitoring that the temperature of this parameter will give you the temperature of the chip. There are different ways, and as I mentioned, it's quite a successful parameter. There are different papers and researchers working on that. And the key is that parameters, if you have access from the gate driver, they are, let's say, good parameters for implementing condition monitoring. You don't care about measuring the power circuit. You just have everything on your gate driver, and that's good. So let's start how you can characterize these internal gate resistance. You can use the peak gate current. So you know that the gate resistance increases with temperature. So that means that your peak gate current is going to reduce. You have to measure this during the turn-on delay. So when your so where your drain source voltage is still high and there's no drain current, and you can use the external gate resistance. So as a sensor, you just measure the voltage across that gate, the external gate resistance. You can track the gate current, the peak gate current. This external gate resistance has to be stable with temperature, and your gate driver circuit is important. So you will require low parasitic inductances, stable output voltages, and fast switching times, because you want to detect the peak gate current. So some bibliography references are there where the circuit was proposed, and some people that use this circuit on silicon carbide MOSFETs. Another way to monitor this internal gate resistance is using a superimposed gate signal. I'm just going to mention this. There's a lot of publications on that, so I'm just going to mention this briefly. So you just use a high frequency signal that is superimposed with the gate voltage during turn off. It's important that the device shall not turn off. So it's an AC signal, and usually they bias the device with a negative voltage to be sure that that imposed signal during the turn off state is not turning on your device. And they managed to monitor the gate resistance. You have a lot of publications where they analyze this circuit for IGBTs, how they designed the gate driver, how they implemented that for monitoring the internal gate resistance of silicon carbide MOSFETs. So if you're interested in this kind of parameters, go through these references that are quite good. And also some people are proposing a DC current injection during the off state. So it also requires a negative gate voltage. Just think about that your gate voltage is off, is -5 volts, and you just inject a current on the gate. So you have the gate resistance and the gate capacity and the input capacitance of the MOSFET. That DC current is going to charge that capacitance. So if you know the resistance, you know the time that it takes to go to 1 volt, 2 volts. If you are below the threshold voltage, you can use that charging during off state to identify the internal gate resistance, and hence you can calculate the temperature of your chip. So there's some references where you can check how this circuit is implemented. I just want to give a brief description of this, otherwise the presentation will be way too long. So the papers are there if you are interested in this kind of circuitry. And there are more parameters, but we have only 1 hour to explain this, and more parameters are still being proposed. So I'm just going to mention some of them very fast. So delays are also parameters, both at TSCP, but they are both TSCP temperature sensitive parameters at both turn on and turn off. Gate plateau voltage. So in silicon carbide, the gate plateau voltage reduces with temperature. It's just related to threshold voltage. So you can see that the delays is just the time from in the turn on is from the moment when you switch on your gate to the threshold voltage, the time to plateau. So you could use these parameters as TSCPs. So I have a question here that is, if you have used TSCPs, which ones you have used these circuits? So thanks. But now I would like to highlight, I presented a lot of parameters, and in some of them you probably would have noticed that the parasitic source inductance was key. It was a key sensor for monitoring determined parameters. So it can be used for monitoring delays, it can be used for monitoring the degradation of the wire bonds. So that's a key parameter for monitoring the degradation and monitoring electrical parameters. So I would say that that's a key enabler for condition monitoring. Is a sensor that is already in your module. And in this publication, they evaluated how the stray inductance in IGBT power modules can be used for monitoring different parameters. So consider what you have in the device that can also be, that is already there. It can be a good option for monitoring the state of health, temperature of the device. So sometimes you don't need a complex circuit. The circuit is or sensor. The sensor is already embedded in your module device. Then concluding, I presented a lot of circuits and a lot of different parameters, but not only the circuit are important. Measurement methodologies are key, and you need strategies for online measurement. So you can decide that you want to measure things during a standard operation, that you want to define some measurement sequences, and this can be important if you want to characterize the thermal impedance. And just some examples of what people have done. I have just 4 references, so how they propose how to do things online in situ, and even some recent papers where they propose the use of a discontinuous PWM for monitoring the on-state voltage on silicon carbide MOSFET. So if you are interested in the topic, this bibliography can be interesting for you. That is not only about designing your circuit, understanding how your TSCP behaves. You also, if you want to implement that online, you need methodologies and strategies for doing online condition monitoring. Now, just to conclude, talking about silicon carbide MOSFETs, and silicon carbide MOSFETs are affected by BTI. So what happens with these TSCPs? Are they going to be affected by BTI? Yes, no. How are our measurements going to be affected? So let's see what happens there. So BTI is related to threshold voltage instability in silicon carbide MOSFETs, and BTI is affected by bias indicate, and it will have implications. It may be both in the application, but it also can be on condition monitoring. So the wrong state resistance is going to be affected. Your switching transients are going to be affected. So the accuracy of the TSCPs will be affected. Some results were already presented in webinar 8, but today I'm just going to analyze this from the point of view of condition monitoring. So as was mentioned in webinar 5 and 8, the impact of BTI is more apparent at low gate driver voltages. That's just the contribution of the channel resistance. So you can see that in the case of a PBTI stress for both a planar and a trench device, if you're driving the device at the nominal gate voltage, so is the impact of BTI is not very high, probably we're talking about 5 to 7%. This may be additional losses. But if you reduce your gate driver voltage, the impact of the threshold voltage shift becomes more apparent. So you can see that with low voltages, you can see a big difference on the resistance. And now I would like to say that evaluating what is the grading during power cycling test are the wire bonds, which is the chip resistance, can be fundamental. And if you have this kind of circuit where you can monitor both the voltage on the chip and the voltage on the wire bonds and evaluate the role of the gate voltage, you can start tracking and identifying what is the grading. Is the chip that is affected by the gate voltage? Is the bond wire resistance, which is not affected by the applied gate voltage? You can start evaluating what is the grading in silicon carbide MOSFETs. People are also proposing, we don't care about temperature, we just want to monitor the electrical degradation. So I want to use my measurements at the zero temperature coefficient point. This is the point that the on-state resistance is not going to be affected by temperature. But what happens with BTI? So if this zero temperature coefficient point is affected by BTI, you may have a problem. So PBTI, you can see that it shifts slightly the ZTC. So now it's around 15 volts. Here it was around 14. It also changes the temperature sensitivities at low gate voltages and at high gate voltages. Negative stress, you have the same around 14 volts, and you can see that the shift, it was highly accelerated stress of the ZTC. Now it's a very low ZTC, now it's around 11 volts, and the temperature sensitivity has also changed. So the threshold voltage shift caused by BTI is moving your calibration curves all over the place. Switching transients, again, they are affected. So BTI will affect the measured switching transients. So you have your calibration curve, you calibrated your switching rate with temperature, but now if you do positive stress, your switching rate is going to reduce. If you do a negative stress, your switching rate is going to increase. So what happens here? So you have this calibration, but then your switching rate is going to be affected by BTI. like also to mention that these are highly accelerated stress tests. So this means that your TSCP is going to lose accuracy. So here in the block is just the initial calibration curve. And then after increasing the stress, you can see how your TSCP has changed at different gate resistances. So the key of this is that you may have the same switching transient and different temperatures. So here is shown the switching transient at 85 degrees for a device that was not stressed, and at 150 degrees for a device that was subjected to PBTI stress. And you can see that, okay, the transient is the same, but in one case the temperature is 85 degrees, in other cases 150 degrees. So what's the real temperature? The switching rate is that, but is my calibration curve affected? So that's tricky. So the gate plateau is also affected. So you can see that it reduces with temperature, with PTI is also increasing because of the change of the threshold voltage. Moreover, the gate plateau was already affected by the load current, and you have the same input of PTI. You may end up measuring the same gate transient in different temperatures after stress. So BTI has to be added as a consideration for condition monitoring. It may be that you just want to evaluate what's the input of the oxide stress in your parameter. It may be that you want to monitor temperature independently. So there are different options there. So last question, and this just concludes the webinar. Thanks. So just concluding, we have presented the challenges of power cycling in silicon carbide MOSFETs and shown suitable power cycling methodology for silicon carbide MOSFETs. We have presented some of the most common circuits for implementing condition monitoring in power electronics, and they include the on-state resistance, threshold voltage, internal gate resistance, current switching rates. And we have introduced the input of bias temperature instability on condition monitoring for silicon carbide MOSFETs and how it will affect the accuracy of the TSCPs. We'd just like to acknowledge Professor Laia Letisse and some academics from Warwick University. We worked together last year in a tutorial at the EP conference based on condition monitoring, and I learned quite a lot during the preparation of that tutorial for the conference, so I would like to acknowledge them. So I would like to acknowledge the funders, the UKRI, for giving me the opportunity to present this webinar, and the previous funders of the research. So thanks for attending the webinar. So let's go to the Q&A now.
Thank you, Jose. That was a fantastic presentation. I think we've got a few questions coming in. I'm just going to, whilst those are coming in, I just want to briefly share my screen, if I may. Your presentation prompted a few thoughts, Jose, about measurement accuracy, and I thought it worth just sharing a typical spec of an oscilloscope in terms of amplitude accuracy. Now, I don't know whether
that's fine.
Yeah, let me just give it a go. I don't know if this will work. It's not that one. Maybe I can share a screen. Yeah, this one will do. Okay. Okay, so hopefully you can see that. This is just a quick grab of part of a data sheet from a LaCroix oscilloscope. I mean, this is generic data across multiple manufacturers as well, but we've chosen to use a LaCroix one as an example here. So when using oscilloscopes to make an assessment about the absolute level of some parameter you're measuring, you have to be aware, certainly, and I remember my supervisor years ago pulling me up on this. We have to understand the native accuracy of the equipment. So I thought I'd just pull this one up here. Now, this is an example of a fairly reasonable quality oscilloscope, and you can see here that the gain accuracy, so the vertical accuracy, is about plus or minus 1% of the full scale, and there are some offsets as well that you sometimes pick up. So I think it's completely valid, certainly, to make measurements using a scope of absolute values, but it's always a good idea to have at the back of your mind the accuracy that the scope is going to give you, and I have a feeling also the accuracy of the scope depends on whether it's not just full scale as well. It's also if you've dialed in to have a very small resolution, like a few hundred millivolts per division, and your signal you're looking at is therefore going off the top of the screen. It comes back to the point you were making earlier, Jose. Then the internal amplifiers in your oscilloscope have to come out of saturation to be able to then report the voltages at lower levels, and that takes time to do, and that's where things like the little the circuit you showed, Jose, that clipping circuit which isolates the front end of the scope when the voltage exceeds a certain level. That's why those sorts of systems are really useful, because it means you can then dial in the accuracy you need on your scope without having to worry about amplifier saturation and things like that. So I think I guess what I'm trying to say here is, don't always trust what the scope says. You should always keep an eye on the accuracy of the measurement you're making, because it can vary from one scope to another. That was my point anyway.
Yeah, I mean, I agree on that. And then sometimes when you want to measure things, you have to be sure that you are measuring the right thing, that you are not measuring noise, that your scope is good enough, that you have filters.
Yeah, exactly.
I mean, saturation is, if you want to characterize the drain source voltage transient and you don't care about those millivolts, everything is okay. Yeah. But if you care about those millivolts, you need that circuit. Some people are proposing that already. So I see that you have put there a clipper. But if you want to implement that into an online condition monitoring system, you will have to design.
Yeah, of course. Yeah, absolutely. Yeah, because the other thing that can sometimes happen with scopes, when you first set your scope up, and you should normally do like a well, it's not even a calibration, it's a compensation adjustment for the probe. That on the front end of a scope, there's normally a little thing you clip your probe onto, and you can change so that changes then the sort of the attack and decay time of a square wave to make sure you try and calibrate your probe to have a nice smooth response, and essentially you're programming the frequency response then of the scope and the probe together. So that's something that people don't often do, but that becomes important. And I do wonder, as we go to really high frequency operation with these sorts of measurements, whether we start to move away from perhaps using normal scope probes and actually use like a 50 ohm buffered, like an active. Well, that's what active probes do essentially. You have an active circuit in there which turns it into a 50 ohm measurement system. But to do that successfully, you definitely need the front end clipper type behavior to protect the system, because it's only going to work at low voltage then. I don't know if I've summed that up well enough. Hopefully you get an idea what I'm saying there is you really need to understand your measurement system and its limitations to be able to do this sort of stuff, I think.
Okay, but I would say that's important also, the skewing. Be sure if you're going to monitor and calculate losses, to be sure that your current and voltage they are in phase. So you just use a resistive load, pure resistive load, and you just check that the current and voltage are in phase.
Yeah.
So let's go to the questions. Let's see what people ask. Any study information available on power dissipation against gate driver losses for the different condition monitoring circuits? Okay, so far I haven't seen any study like this. So they mentioned that in the case of the diode circuit for measuring the on-state voltage is quite important that you manage to keep the temperature of the diodes the same, that your diodes are not getting hot. So your diodes are going to be biased during the on-state voltage measurement. So if your diodes get hot, so your voltage can be affected. And if they have different temperatures, your measurement can be tricky. So it's really, you remember that it's just the voltage difference between the diodes. So if that voltage difference if there's a voltage difference there, and the voltage is not the same, your on-state voltage measurement can be affected. And then I saw some in the papers and attended some conferences when they analyzed the gate driver circuitry. But they focus more on presenting the methodology rather than presenting power dissipation or additional circuitry on the gate. So I would say just try, if you are interested on that, just try to follow the researchers. Hopefully I didn't went too fast, and with the video you can stop and try to do a search, and that can be interesting. For that, I mean, there are a lot of people working on condition monitoring and circuitry, and things change from one day to the next, and people are proposing a lot of things. Just check the successful ones, what people are, if people are using what other people propose. So that's always a good indicator. And the other one, okay, there's also another question there. So, but let's go with the second. Are there any issues that you have noticed where switching operations of complementary devices, half bridge, full bridge, under hard and soft switching, and consider their time that affect the fidelity measurements from condition monitoring circuits? Okay, so the main trouble that you may have when you are switching is that you may have noise coupling. So you may have high DVDT transients, and you may end up measuring noise that is not there. So if sometimes you're going to have ringing, and that ringing is not there. It's not some ringing that will appear on your circuit. It's just coupling because of EMI. You have a fast DVDT. So I think that we are planning to have a webinar on tricks for measuring things properly in the application. I think that was the plan, Ian, if you can correct me.
Yeah, that's right. We haven't published that yet, but that's going to be, I think, webinar number 19, if I'm just looking at the board here. So that'll be at the start of, probably the start of December. So practical tips and tricks, that sort of thing.
And then I will also say delay times when you're going from 400 volts to low voltage, saturation of the op-amps. That also happens with the oscilloscope. If you have large leads, then you have coupling there. So that could be something there.
I think half of the battle with this sort of this subject is that ability to know whether your measurements make sense or not, or is it the equipment, or how the equipment is being utilized. You know, it's quite difficult to make these measurements, I think. So you really need to understand how equipment's operating to be able to understand whether there are any problems or not. I had
yeah, and there's another one.
Oh, okay.
There's another question that is quite interesting. Is can the gate leakage current during on time be affected for condition monitoring aging? So that's an interesting question. So what happens? I mean, it can be used, but you have to remember that the gate leakage current is going to be very, very, very small. So if your gate leakage current is in the range of microamps, something like that, you are already into trouble. The gate leakage current should be nanoamps. It should be really difficult to measure. However, I presented something regarding GaN devices at some conferences EP this year. Some people are working on similar stuff in other conferences that I attended. In GaN devices, the gate leakage current is quite high, and they are already proposing the leakage current as a temperature-sensitive electrical parameter. And it's curious that one paper that we were working on the same, absolutely independently, they propose a circuit to monitor that. So I would say that depends a lot on the device, and the gate leakage current on silicon carbide devices can be tricky and very tricky. I mean, if your gate leakage current is going to go to the levels that you can measure, probably you are way beyond your reliability point of view, reliability point of no coming back. So your gate leakage current is 1 milliamp, your device is not healthy. So it can be just a way of checking. Some people identifying short circuits if the gate leakage current starts to increase. So your gate is damaged, but at that point, your device is probably damaged. It's not monitoring when the device is at the end. You want to monitor temperature during standard operation with a healthy device. You don't want to say, okay, my leakage current is way beyond this device is faulty. You want to do things before getting to that point. How to say, that's my point of view. But with GaN, it's quite interesting that the gate leakage currents are quite high. Some people are proposing that already as an indicator, and there are some circuits that you can use that for monitoring temperature and aging.
Jose, this is this subject. It's really interesting. It's prompted a question from me, if I may. So we've talked quite a lot on the presentation today, all about the sort of the parameters you can measure to indicate the condition of the device, which is the fundamental subject here. Have you got any awareness of the research in the other side of this, essentially the sort of the artificial intelligence, and how that data can then be utilized to make a decision about whether a device is good or bad? Because I can imagine you want to do that accurately. Maybe you want to use data from multiple TSEPs, or knowledge of ambient temperature. There's going to be some sort of calculation engine that sits somewhere in your system, taking all this data, that has to form a decision about whether the device is good or bad. Are you aware of research in that area, which is in artificial intelligence, that sort of thing?
Yeah, some people work on that. So the key here, that topic, I would say, let's put my video on for a while so you can see my face. So the key that I would say is that what do you want to monitor? Do you want to monitor the converter, or do you want to monitor just a chip, a MOSFET? So what I presented here, it was just a single device. You have to remember that in modules, you're going to have different chips that may have different temperatures. So in some cases, there are some artificial neural networks that some people are monitoring the different parameters, and they understand how is the current shared between devices. Also, I didn't put it here, but if you have different chips, what is the TSEP given to you? Is the average temperature, is the peak temperature? So things that are like that. Also, going back to BTI. So what is the grading? Is it temperature or is it gate oxide? Can you operate at some point that I use this parameter for monitoring the oxide degradation? Like the BGS, the body diode that BGS equals 0, that is affected by oxide, but you need to know the temperature. That was covered in webinar 8. Do you want to put the gate source voltage at -5 and just use that for measuring the temperature? Do you want to, what happens now in your converter, that imagine that you have a power module, that is, I think the resolution is glitching. So what happens if you have a power module that is an inverter, that you have 6 chips, and the power factor affects the dissipation of the different chips. So now what is getting hot is the diode, it's not the IGBT or the MOSFET. So some people are proposing different thermocouples. So if you just identify that the temperature of the different thermocouples and the inlet water temperature, but still you have to train your, people say artificial intelligence. Artificial intelligence requires training.
Exactly. Yeah, exactly. It needs some sort of basis to make a decision on.
So you need to understand what is expected, what is not expected, it's like thermal camera. A thermal camera image is brilliant, but you have to do 2 things. You have to remove the gel, otherwise your thermal image is not good. And you have to coat the power devices, or you have to coat your converter, otherwise your measurement, you don't know what you are measuring. Also, would you say that, can you use power losses as an indicator? Power losses are affected by the state of health. So I would say, I work on devices. I like working on devices and work on this structure, but are people really worried about devices, or people worry more about the converter operation? So is there any indicator there that is, from the converter point of view, that is going to give you the state of health?
Yeah. Because if you think about,
because I can tell you, okay, it's a chip. Yes.
Yeah. Because if you think about it, from a manufacturer with a product in the market, the thing they care about is if they have a sort of any requirements on guarantee of uptime, for example. They might have financial penalties, or they might have warranty issues if something fails too quickly. So I would imagine this sort of technology would allow them to more accurately know when something's going to fail. So, and the more accurately they know that, then they can actually replace it in the field before it fails. But they don't want to replace it too soon, because otherwise you're wasting money as well. So I suspect at the end of the day, manufacturers will care about systems and reliability of systems, but this is probably a key underpinning part of the reliability of that system that can be used to predict. But this comes back also to the question I made a moment ago. Maybe the data analytics that you can get from the monitoring the TSEPs in the semiconductors are combined with the historic knowledge of the operating temperature of maybe the rest of the converter, or knowledge of the input voltage, or some other set of parameters to form an overall decision. Is this converter about to fail or not? And that's probably what the manufacturers are interested in, I would think.
Yeah, I mean, it's like if the ambient temperature changes, your device temperature is going to change. I mean, it may happen that you have your converter in a cabinet, the fan of the cabinet is broken, and your chip temperature is increasing, but it's increasing because of the cabinet ambient temperature increasing. Yeah. There's an interesting comment here. So if you go to the chat, there's some comments when we are speaking. It's just depending on the algorithm applied, supervised and unsupervised. So they agree that circuit system operation is more important from product perspective than device status. So device status, I would say device is important, because at the end, if you have 16 chips in parallel and one device fails into short, that's not good. That's your converter going into short.
Yeah.
So, but I think this is a interesting area. So, because will people that are working on systems level care about what we are doing at device level? So, or are we just overkilling condition monitoring? People who are just saying, "Oh, you need to know the temperature of the chip."
Yeah, I think they will care about it, but not necessarily how you know about it. They probably won't care that it's a TSEP or something else. They'll care that they have an ability to understand the stress that device is that semiconductor is being placed into, and maybe they can then feed that information into some broader algorithm which allows them to make a sensible decision about their product state of health, if you like. So I think they would be interested, but yeah, they'll not worry too much about how you do it, as long as it's reasonably accurate.
Yeah. Well, interesting. I hope that people enjoyed my last webinar, so I don't have to speak again. So hope that you enjoyed the webinars that I presented. So thanks to Ian for giving me the opportunity to be part of this. I quite enjoyed presenting. I hope that I managed to share a bit of my knowledge. I know I don't have a lot, but if you manage to enjoy and learn something, I managed to make people aware of what's going on, so I'm happy. So thanks for that.
Thank you, Jose. You did a fantastic job today. Thank you very much for joining us on this.
It looks like the chat is interesting today. It's an interesting conversation on the chat, if you think about this. So it looks like that we have triggered some interesting discussion. If this was a face-to-face tutorial or face-to-face conference, probably we will having a interesting chat after having a coffee or during the coffee break. So
yeah.
one day we will be back onto face-to-face conferences, hopefully.
yeah, that will be good. Thank you, Jose, and thank you everybody for joining us today. Keep an eye out for future events. We've got about another 5 to go to take us through to the end of the year. So thank you for joining, and we hope to see you soon. Bye-bye.